Hello, I'm Suzanne Herring, and I'm pleased to be here with Professor Kim Prather from the University of California, San Diego. And Kim has had a very active career in aerosol science, mostly with her aerosol time of flight mass spectrometry. Uh, and I've known Kim for 15 years now? No,
20,
20 years
20
now.
years, yeah.
20 years now,
Yeah, at
since
least.
she was a young assistant professor
That's right.
at University of California, Riverside at
Hmm.
that time. And Kim, I know you had a rather interesting pathway to becoming a university professor. So why don't you fill us in a little bit about that?
Well, I think one of the questions people often ask me is, did you always know you wanted to be a professor? And my answer to that is a resounding no. In fact, it was no way.
Yes.
I, really, started out, sort of in, high school, wasn't really that interested in, I hadn't really found my niche yet, and had a terrible chemistry teacher and thought I would never, ever go into chemistry. And and so then I wasn't even sure that I wanted to get a bachelor's. I went to a junior college to give myself a couple of years to figure out what I wanted to do. And I was a tennis player. I played softball. Those were my priorities. I basically wanted to be a secretary, a legal secretary. But was on the path. I thought I could get a 2-year degree and just go get a job and keep my sports career going. And so I ran into a very influential chemistry professor at the junior college who sort of taught me one of my big life lessons, which is I do best when I'm challenged. And so chemistry finally started to be hard and challenging, and I took off in chemistry. And so I quit the tennis team and kept playing softball, only at night though. And I ended up going through for heading more towards chemistry, and then transferred to UC Davis as a chemistry major. Still thinking, okay, at this point, I'm just going to get my bachelor's now. That was a stretch. And then I ended up, then I still wasn't sure what I wanted to do at the end of my bachelor's, and had a professor try to talk me into staying for a master's. It's only 2 years. You can stay for a master's. Okay, I'll stay for a master's. Never a PhD. No way. And the next thing, I stayed for a PhD, and all in chemistry, just hardcore, fundamental physical chemistry. So very far from the aerosol world. And so in the end, I ended up doing a postdoc with Professor Yuan Li, a Nobel Prize winner in physical chemistry at UC Berkeley. And that's when the light bulb sort of just started to flicker that maybe I would be a professor someday, but still not really sure, still thinking industry might be a better, more balanced life, whatever that is.
And you were still playing baseball.
I was still playing. That's how I got to work for White Healy. He picked me because of my softball playing skills. And so we played softball and I did science. And in the end, I really, again, it was very sort of, I almost I was very sure I didn't want to be a professor until the very, sort of late stage. And then all of a sudden, it was sort of around the time where I decided, I don't know if I should say this, but anyway, okay, I'll say it. I kept applying for industrial positions, and I kept getting offers, but Professor Lee didn't want to support that. And so one day he called me in his office and told me, I want you to be a professor. I'm not sending in those letters of recommendation. So there it is. That's why I became a professor. It was the only job. It was the only. I've never ever had this taped before, but it was the only job that he would support me for. So I had to come up with a job proposal, and I really wanted to. I knew what I really want. That I had been doing fundamental chemistry, which was fine. It was great training, but I knew I wanted to do something that would help the real world. Something environmental. And at that time was around the time when the ozone hole was discovered. And it was shown at that time that it was particles up in the stratosphere, way up there, that were actually changing the composition of the stratosphere in a major way. So I thought, if particle surfaces are important in the stratosphere, then they're going to be really important in the troposphere. And there was also work being done at that time on surfaces related to sea salt by Barbara Finlayson Pitts. So I thought, well, I want to study this a different way. So I'm going to go buy an instrument that lets me look at reactions as they're happening in real time. And so I started to propose to buy that instrument and started looking for that instrument, and it didn't exist. And so I ended up having to basically propose to build the instrument. And there were papers dating back that Sinha and Friedlander had actually tried to make this happen for many years. They'd kind of got it to happen, but there were little parts that didn't quite work. And so I focused and figured out a plan to make it work. And yeah, so
building on their experience.
Building on their experience, but taking advantage of the technological advances that were there. There was just certain things that, the speed, data acquisition, things weren't quite up to snuff, and it made theirs, they were almost there. And then I just sort of took the pieces together of a few different ways of doing things, and then basically proposed that as my job, what I would do as an assistant professor. And so my first, sort of 10 years or so was getting that instrument to be built and working and calibrated and applying it to problems.
So you were sort of the first one who measured that probability density function that Friedlander wrote about in his book, where you say for each particle what its size is, what its chemical composition is, and what's the probability of finding similar particles in the atmosphere.
Yeah. So a big push for us has been to do just that, sort of what they called sort of the perfect measurements, right? It was like to be able to actually get everything about one particle, including, a big push for us at the beginning was really to understand the sources. So to take that one particle, blow it up essentially, and get a fingerprint, a chemical fingerprint that we could then link back to the source. So it was not just the composition, but a little bit more about tying it back to where did that particle come from? What's been its history in the atmosphere? Has it aged? Has it gone through over a cow farm? Or, what is it, how, sort of how reacted has it become over its lifetime? So getting something more information on the source and degree of aging was a big push for us.
And the other aspect was the time resolution.
Yes, that's right. Yeah. As fast as you can.
Because up to this point, people were just doing filter measurements, or maybe the sophisticated one were impactor measurements to get size resolved chemistry.
Right.
And you never knew the answer for months.
Right.
Months. And I had always had a goal, my own personal goal, of looking at particle chemistry in closer to real time.
Right. Yeah, that was definitely, one of the things we really came to appreciate was that, all the particles, there's a great diversity from one particle to another, and those change pretty fast. And so we didn't even know how fast at the time, but when you lump all that information together in size and in time, and mix all the particles up, it's really challenging, as we've found, to try and unravel, sort of tease out how it changed over time and over size, from a source, different sources.
And as an example, one of the things I recall that you did early on was tracing the nitrate particles across the LA basin.
Yeah.
And I remember when I was down there with my little nitrate measurement system, we would call each other on the phone.
That was exciting.
Hey, the nitrate just
Those
went
were the days.
way up.
Those were the days. Yeah. We were going back and forth. The students kind of thought we were a little crazy because we were like hooting and hollering.
I would see the total concentrations in a quantitative way, and you could tell me what size they were. Oh, they came in the coarse mode. Oh no, this is fine mode nitrate. Well, and then you trace where the differences came from. You want to talk about that?
Yeah. So a little bit more. And like one of the things, a lot of people had seen, especially in Riverside where pollution builds up, they would see these like nitrate would triple, Okay, why? And we were able, when we were going back and forth, you would say, all of a sudden the nitrate went up. And I would look and I'd say, but it's ammonium nitrate and it's on organics. Or I would say, oh, it's all on sea salt. It's sodium nitrate. So we could actually say, did it get there through heterogeneous reactions? Did it get there through condensation? So we could actually tease out more of the mechanism of why did the nitrate, not just that the nitrate went up, but why did it go up and where did it come from? That experiment was a very special one for me. And that was 1996. That was the first real field study we did. Was with Glenn Cass.
Yeah.
And he was a great man, my very first, very special collaborator who, without him, I don't think I'd be sitting here right now. He really, I didn't know anybody. I came from a field of fundamental physical chemistry. I didn't know anybody in the aerosol field when I started. And I met Glenn at a AAAR meeting very early on. And he was just such a special man. And there's a few things that, sort of struck me. We were developing this new way of doing things, and that had some good responses and some not so good responses from the community. People who've been doing filter-based methods for a long time were, kind of like, well, kind of what's going to happen, what's going to happen? How are you going to bridge? How are you going to prove? How are we going to understand anything when they almost seem disconnected? Glenn had a really, really refreshing and positive view. In fact, I remember one day, He's like, I want to help you. I want to work with you. And we're going to do a study together. And we're going to get your instrument calibrated. So it's quantitative, which is what people said would never happen. And so we're going to run our standard size resolved composition Moody impactors, and I didn't even know what a Moody was at the time, against your measurements, and we're going to quantify and basically the amount of nitrate on these particles as a function of size. And we're going to go out in the field and we're going to pick 3 sites, and we're going to sample the air as it starts at the coast and it blows over an inland site and then blows to Riverside, ends in Riverside. And I was just kind of baffled that you could even predict where the air would come, and look at the changes. And so I went along with it. We went along with it. We put instruments out at multiple sites. This was working with CARB. California Air Resources Board had given us the funding to build more instruments. Yeah. And we were able to do that. We were able to see the fresh particles, and actually they blew right where Glenn said they would. And so it was really, really spectacular to do that. I mean, I had no idea, that you could actually do back parcel trajectories and say that the air came from there 4 hours before, or the air spent this much time over land. And so, but he was just, as I say, I think he was just a very special person at that time, in that he didn't care that he basically said, I want to get your instrument calibrated so I can throw mine in the junk heap. Those were his words. I was just shocked, at that open mind. Also, it was very clear to me that he was a man who just wanted to get the right answer. Whoever got it, how you got it, he didn't care. He just wanted to know the answer. And that is a very refreshing attitude for someone to have. He's a very, very special man, but he made a huge difference in my career.
Yes. All of us remember him very fondly.
Very special. Yeah.
So then after some number of years, and your instrument is beginning to be seen as a pretty successful and useful tool, you got recruited to UC San Diego, as I recall.
Yep.
And there your research area took a slight shift.
Yes, it did. I mean, so the first part, of my career, the first 10 years, as I say, or so, were spent on, getting the instrument working and calibrated. And then it's like, I just wanted to do something. You could have kept refining and making it better and better, but I really wanted to go answer questions. So the first questions were just related to sources and air pollution. And that was Riverside days, really focused more with a twist on human health and identifying what are the sources that make up the pollution. So then when I got recruited to UC San Diego, I went there because of Scripps Institution of Oceanography and climate. And that I got pulled there because I had met Ram Ramanathan and Paul Crutzen showed up at my lab at UC Riverside and said, we would like you to move to UC San Diego. And so, and so I ended up doing a field study with them first, Indox. There we identified the source of the brown cloud. That was probably one of our biggest findings, certainly internationally, was we were able to show that it was biofuel, biomass. It was controversial at the time, but we showed it was all this burning that they do there.
For the audience, tell them where Indox was.
Oh yeah, Indox was an experiment done over the Indian Ocean. Yes. And we were actually on an island in the Maldives. And a little tiny island, there's still an observatory, very active observatory there today that's being run now by other groups. But basically, it's in the Indian Ocean. So we had our instruments on an island there. There was also measurements done on a ship around for the intensive part. The Ron Brown ship was there as well. And so it was airplanes. And it was my first experiment where there was airplanes and ground and a ship.
1998?
It was 1999. 1999, was Indox. So the Indian Ocean Experiment is what Indox stands for. And so we did Indox, and that's how I got to know them better. And they kind of were working on me to move for a while. And then I finally moved in 2001. And I took it. I wanted to start doing something. I was very interested in climate change. It turns out aerosol mixing state, which is what we measure, is really how the individual particle composition affects clouds is the largest uncertainty in all of climate change. It was then, still is. And so we really wanted to understand how particle size and composition affect clouds and ultimately how they affect climate and precipitation. And so my focus in my research group for the last, since I moved there in 2001 has been really on climate impacts of aerosols and also just regional climate and weather and water is where we really are right now.
And you're looking at the source of these particles again,
Mm-hmm.
and their aging processes, and of those particles that affect the clouds.
Right, right. So what we do, which has been the most exciting measurements of my career, I think, is we look at the aerosols that are available to seed a cloud. You know, what's their size, what's their composition, what's their source, and we fly sort of the ones that are in position to actually go seed the cloud. So, you know, those particles, any one of those, you make either the cloud droplets or the ice crystals, right? So we look outside of the cloud, we say, okay, this is the particles outside of the cloud, this is the sources. Then we fly through a cloud and we sample the cloud droplets and ice crystals one by one, very fast. And we link those to sources and see if there are special ones. Are there certain sources that are better at seeding clouds? In particular, one of our main foci right now is, are there certain particles that are making ice? If you care about precipitation, ice is everything. And only 1 in a million particles on average makes ice, an ice nucleus. And so what is special about those? And so we're really focused on sort of looking at which particles form clouds. And then ultimately, you know, if you find certain sources like dust or biological particles like bacteria in a cloud, does it change the amount of rain or snow that you get out of that cloud? And the answer appears to be yes. And this has been one of the most, as I say, to me, the most exciting part of my career has been taking, you know, atmospheric chemists working side by side with meteorologists who at first thought we were a little crazy. Like, who cares what seeded the cloud, right?
Yes.
The cloud's going to rain, it's going to rain. You know, why would you think? I mean, they kind of thought I was a little crazy at first, you know. So we walked a very delicate line of, well, we want to see when and if the seeds matter. You know, maybe they don't. You know, that's still a finding, right? So we took it very carefully and cautiously. Gradually, many of them have become converted to believing that the seeds do matter under specific conditions. And so, in fact, our findings are now, which is very exciting to us, our findings are being incorporated into weather forecast models.
Oh, so that's interesting.
Yeah. Yeah. So the biggest out of those studies, one of the biggest findings we've had, maybe the biggest of my career, I think, the thing that was the biggest surprise of my career, I think, to date, was we were able to show, we were flying over clouds over the Sierra Nevada mountains, which is where our snowpack for California, where our water supply is stored. We know people had noticed that the snowpack was decaying. And so there was a hypothesis out there that it was our pollution that was going up into the clouds and we were creating too many seeds. And then those seeds, basically the droplets could not grow big enough to fall. Yeah. And so that's what we went looking for. But instead, we found out that that basically particles that were seeding the clouds over the Sierras were coming from as far away as Africa. And in fact, changing and giving us more snow on days when the dust made it all the way across the Pacific. So it was a pathway that people hadn't really thought about. The seeding was actually happening at relatively high altitudes. And that was the switch. On days when the dust from Africa or China, mostly from Africa at that time of year, and biological particles that could have come with the dust, but could have also come from the ocean, we now believe, on days when those were present and you had ice in the clouds, those were the days where you had the most snowfall on the ground. And so we published a paper in Science saying that, you know, dust from as far away as Africa changes snowfall over California. I mean, who would have thought? Yeah, we had a lot of pushback on that at first because most people thought that the dust came from Asia and not until the springtime, certainly not in winter. Yeah. So it was a big push for us. So it's a pretty exciting result.
Your career has been centered around the aerosol time of flight mass spectrometry, or ATOF-MS. Mm-hmm. So tell us a little bit about what it measures, how it works.
Yeah, so what it does is, it basically measures the size of particles aerodynamically. There were about 3 or 4 groups at the same time that ended up sort of trying to go after this size, composition, fast link. And we were the one group at the time that decided to do aerodynamic sizing as opposed to optical sizing. And that turned out to be kind of a magic twist because that gave us very precise size, just like the aerodynamic particle sizer. So it aerodynamically sizes each particle. And then by knowing how fast the particle is moving, you know, by tracking that particle moving between 2 laser beams and getting the speed, we can time when it gets in the center of a mass spectrometer and we fire a laser and blow apart that particle into its components. One of the other unique things we have in the ATOF-MS, but now many other people are doing this, is we actually, as opposed to just looking at positive ions that form chemically or negative ions, we actually built our first instrument to look at both. And so that was unique. So the sort of the unique part of the ATOF-MS is the ability to aerodynamically size each particle as opposed to optically size, and the ability to get both positive and negative. And it turns out that getting that positive and negative information has been absolutely critical to what we do. The positive ions tend to give you information on the source. And so it tells you if there's metals present, if there's soot present, if there's organic carbon present. Whereas the negative ions tell you about the nitrate, the sulfate, the chloride, the aging. So they're just totally complementary to be able to look at both. And so that's the unique thing about the ATOF, what we call the ATOF-MS.
Yeah.
Did that answer it? Did that tell you?
I would say there was another unique aspect of your instrument, and that is you went very quickly from this instrument that filled your whole lab at Riverside to something that would fit through a 30-inch door. I like the generations idea. Yep, that's boy, you remember this. That's exactly right. Yeah, so we started out. Yeah, the first instrument filled a lab literally, and it was called the Beast. Remember? Yes. Remember the Beast? The Beast still exists. In fact, the Beast is now in one of my former students' labs, starting his job as a professor, which is kind of special. So the Beast has come back to life again, which is great. My gosh.
So there's a Beast in someone else's lab now, and there was Beast, and then we had proof of concept, and then the California Air Resources Board became very interested. And so they came and funded 2 transportable versions of the instrument where we put it on a rack with wheels. And as you say, we're able to push it through a door. Still big, but that was the beginning of Jake and Elwood, the 2 transportable. We used to call them portable, but we decided transportable was more accurate.
It did take a truck.
It did take a truck, truck, so we had Jake and Elwood. And then working with TSI, actually, we developed, around the time when they commercialized the instrument, we developed Laverne. And Laverne is just a smaller version, a more petite version of Jake and Elwood. And then, so she's just a smaller version of Jake and Elwood. And then the next generation was Shirley. Shirley came after Laverne. And Shirley is the aircraft instrument that fits on an airplane very well. Even more petite. That's when we went to what we call a ZTOF, a different type of mass spec that lets us have a folded path of the ions. And so that's Shirley. So that's been the multiple generations. And now we're making another version that's even smaller. I mean, we would like to make a version, our dream is to make a version that can go on UAV platforms so that that's really small. That we can fly to clouds and do a lot more. So yeah, that's our we haven't given up yet. We will get there.
I'm sure you will. I mean, given how you went from the Beast to the Jake and Elwood.
Yep.
I remember those 2. And then
Laverne,
each time is
smaller and smaller.
We're not talking about 20% smaller. We're talking factors of 2 or 3 smaller.
Or 4, yes.
Or 4.
Yeah.
Well, the first one was
gigantic. Yeah, the first one was huge. But yeah, we're talking each time was at least a factor of 2 smaller. And we've still got another chunk to go. And we have ideas now on how to do that. So more to do, job security.
So Kim, I think one thing in the years I've known you, it's been quite a few, the constant in your career has been your enthusiasm. And it's certainly driven all your work, but you've also mentored a lot of students.
I have.
And so I'm going to ask you, as you look at the young aerosol scientists and those who might be watching this video, what advice you have for them as they go forward.
Oh boy, I get asked that question a lot these days. I mean, one of the most rewarding things to me is to watch my people going out into jobs, and they're getting very good jobs these days. It's really, really rewarding to see this, and it's reassuring to me to know that I don't have to work until I'm 150 years old to solve the problems. They're going to take them on. They're ready to take them on. My students have been fearless over the years. But the advice I give people is two pieces of key advice. One is to not be afraid, there's nothing you can't do. If there's something that hasn't been measured before, it doesn't mean that it's impossible. We've had a lot of pushback at the beginning when we said we were going to build this instrument. People said, well, the instrument is so needed, it must be impossible then. And nothing's impossible. And I've taught my students through the years, one of the key things is there's a way to do it. If you have a question, figure out how to answer it. If there's a way to do it, buy it. If there's not a way to do it, build it. And so be fearless though, really Just don't be afraid, because you can make anything work if you put your mind to it. And so that's the first piece of advice. My second piece is what you said. What's gotten me through is really my career. It doesn't feel like work. It's fun, and I have a strong passion. I genuinely care about the science that we're doing. I personally am motivated, and I think most of my group is motivated by the fact that what we make, I mean, this was always a dream and almost didn't seem possible, is what you measure in the lab or in a field study can actually translate to help real world problems. And that, is what gets you out of bed in the morning. In particular, I have two teenage boys. We have a responsibility to leave this world in better shape than it's sort of currently heading right now, I think. And so, I feel personally responsible to understand what is going on and to come up, hopefully, with solutions to make it head on a slightly better trajectory before I'm done. And so I think that feeling of, finding something that you love, then it's not a job, right? It is, you want to go into work. You're sad when it's time to stop at the end of the day. And that, I can't believe I get paid to do what I do. I mean, I absolutely love what I do. And I love being able to help. And I love, the training of the students and the science. I mean, it's an amazing job. So.
Well, thank you very much.
Is that good? Thank you. Thank you very much.